Light does not rush without limits. Even now, as you listen, every photon traveling through the universe moves at the same quiet maximum, a cosmic speed written into the structure of spacetime itself. Nothing with mass can ever reach it, and nothing without mass can ever slow below it. This boundary is not a suggestion. It is a fundamental truth, older than stars, woven into the very geometry of reality. Tonight, we drift into that truth with gentle steps, exploring why the universe chose this number, why nothing outruns it, and what unfolds when motion approaches the edge of possibility. If this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps this quiet corner of the universe keep glowing, and your presence means more than you know. Now we drift into the first set of ideas, 15 quiet doorways into a story about speed, light, and the limits written into nature. Part 1. The Silent Constant. Why light moves at one universal speed. Everything else in nature changes. Stars brighten and fade, atoms collide and drift, but the speed of light never wavers. It is the same in every direction, in every vacuum, at every moment. Tonight, we step gently into why this constancy exists at all, and how the universe shapes itself around that single unwavering value. If we begin with the simplest question, why does light have a speed at all? We find ourselves drawn into one of the most delicate structures in physics. Light does not travel at its speed because of anything inside the photon. It travels at that speed because of the nature of the medium it moves through, spacetime itself. Even though spacetime is not a substance you can touch or feel, its fabric carries rules, just as water carries currents and air carries sound. In the quiet mathematics of electromagnetism, the speed of light arises naturally from how electric and magnetic fields interact. It is not chosen, it is not adjustable. It is the only speed at which a self-sustaining wave of these fields can exist. James Clerk Maxwell discovered this long before anyone understood relativity. When he wrote down his equations describing electricity and magnetism, he noticed they predicted a wave, an oscillation traveling at a fixed speed. That speed turned out to be 299,792 kilometers per second, a number astonishingly close to the measured speed of light. Maxwell realized something profound. Light is an electromagnetic wave, and because the equations determine the wave's structure, they also determine its speed. The universe simply follows the mathematics. But Maxwell gave us only the first clue. The deeper reason lies in Einstein's insight, which revealed that the speed of light is not merely the speed of a wave, it is the speed limit of causality, the fastest any influence can travel. In Einstein's view, nothing moves through spacetime faster than light, because light's speed is a property of how spacetime measures distance and time. The units we use, meters and seconds, are not universal truths. They are relationships defined by how light behaves. If you change the speed of light, you would not simply make photons travel faster or slower. You would change what a meter is, what a second means, and how the entire geometry of reality fits together. So when we talk about the speed of light, we are not talking about a mere velocity. We are talking about the scaffolding of the universe. If you could drift through the cosmos without mass, free of inertia, free of resistance, you might imagine you could accelerate until you matched the photon's pace. But the moment you have mass, even the quietest trace of it, you are bound by rules the photon never faces. To move faster, you must push harder. And as your speed increases, your energy grows disproportionately. What we call relativistic mass is not mass increasing in a literal sense, but energy altering the geometry of your motion. As you approach light speed, the energy required to accelerate further grows so rapidly that it diverges toward infinity. Nature gently steers you away from the boundary, not violently, not abruptly, but with a smooth resistance that rises endlessly. This is the universe telling you. You may approach the limit, but you cannot cross it. Even more strangely, the speed of light is the same for everyone, everywhere. If you run toward a beam of light, you do not see it coming faster. If you run away from it, it does not slow down. It is as if light refuses to acknowledge your motion. To make this possible, time and space must shift for you. They must stretch, contract, and rearrange themselves so that the speed of light remains unchanged. Imagine standing still while someone else passes by you at high speed. Their clock ticks slower relative to yours. Their length in the direction of motion becomes shorter. Their perception of simultaneity, what counts as now, warps differently from yours. Yet both of you will measure the speed of light as identical. Space and time bend quietly, not as distortions, but as requirements to preserve this cosmic rule. The constancy of light speed is the universe's way of weaving time and space into a single fabric. If we zoom into the microscopic world, the story becomes even more intricate. In a vacuum, pure, empty space, light always moves at its maximum possible speed. But in materials such as glass, water, or crystal lattices, light can appear to slow. This is not because space-time hesitates or because photons lose determination, but because they spend time being absorbed and re-emitted by atoms. The true limit never changes. Only the path becomes cluttered. Even here, the fundamental speed remains intact in the background, unbroken and unbreakable. This constancy has consequences that shape every layer of reality. The stability of atoms depends on it. The color of stars depends on it. The structure of galaxies, the propagation of gravity, the uniformity of cosmic expansion. Each of these rests on the unwavering rhythm of light speed. If that speed were even slightly different, the universe would be unrecognizable. At a faster constant, chemical bonds would form differently. Stars would burn hotter, faster, or not at all. At a slower constant, the balance between quantum motion and gravitational collapse would shift, possibly preventing stars from forming altogether. We do not live in a universe where light simply happens to travel at its speed. We live in a universe that is only possible because it does. And yet, as fixed as this value seems, physicists still ask the question, could the speed of light have been different in the early universe? A few cosmological models propose that shortly after the Big Bang, during the first moments of cosmic inflation, the effective speed of light might have differed because space-time itself was in a radically different state. But if this ever occurred, it happened before atoms existed, before galaxies formed, before any stable structure emerged. Whatever history the speed of light might have had, by the time the universe cooled enough for matter to form, the constant had settled into the value we measure today. When astronomers look across billions of light years, they see photons that have been traveling almost since the beginning of time. These ancient messengers carry not only images of distant galaxies, but confirmations that the speed at which they departed is the same as it is now. Across the entire observable universe, from the earliest stars to the cosmic microwave background, nothing contradicts this constancy. The limit is universal, not local. It is not something that belongs to our corner of the cosmos. It is embedded in the structure of all of space-time. Somewhere, deep under the equations, lies an even more subtle truth. The photon is massless. But massless does not mean empty or trivial. It means the photon must always move at the speed of light. It has no choice. If it slowed down, it would gain mass, and gaining mass would violate its very identity. In a way, the photon is not racing. It is simply existing in the only state it can inhabit. Light does not try to reach its speed limit. It is the limit. And as we consider this constant, silent, unwavering, ancient, we begin to sense something profound. The speed of light is not simply a number written in textbooks or an artifact of mathematics. It is the quiet pulse of the universe itself, the rhythm that keeps time coherent, distances meaningful, and causality intact. Without this constant, there would be no before and after, no clear progression of events. The universe would have no stable geometry. Motion would be undefined. Reality would lose its ability to communicate with itself. So the next time you think of light, imagine not just a photon crossing the void, but the entire fabric of existence maintaining its most delicate balance. Light does not travel through space. Light reveals what space is. And as we continue this quiet journey, one question naturally follows. If light is bound to this constant speed, then what happens to anything that dares to approach it? Part 2. The fabric that sets the limit. Spacetime as a medium. If you could run your hand across spacetime, you would find no surface, no texture, no vibration. Yet it behaves like a medium with rules. The speed of light is not the speed of photons, it is the speed permitted by the geometry they travel through. Here we explore how spacetime itself imposes a cosmic maximum. To understand this strange medium, imagine a vast expanse that is not made of atoms, molecules, or particles, but of relationships, distances, durations, and the invisible connections between events. Spacetime is the framework that allows anything to happen at all. Without it, there would be no paths for motion, no order to time, no way to measure separation between one thing and another. And yet, this framework is not passive. It shapes the rules that everything within it must obey. At the heart of these rules lies a relationship between space and time, so intertwined that neither can be understood alone. Einstein's theory of relativity revealed this unity. He showed that space and time are not independent dimensions, but a single fabric. And like any fabric, even though you cannot grasp it physically, it determines how things move across it. A ball rolling across a smooth surface moves differently than one rolling across sand. And in the same quiet way, objects moving through spacetime experience the structure of spacetime itself. This is where the speed of light enters. Light moves at the speed that spacetime allows for the propagation of information. It is not that photons accelerate to this speed or maintain it through effort. Instead, they follow the paths drawn by spacetime's geometry. In the equations of relativity, the speed of light appears as a constant that ties together how distances and durations relate. If this constant were altered, the entire structure of reality would shift with it. To see why spacetime sets the limit, we can imagine dropping a pebble into a perfectly still pond. The ripples move outward at a speed determined not by the pebble, but by the water's density and surface tension. No matter how hard you throw the pebble, the waves cannot exceed the water's inherent propagation speed. Spacetime behaves in a similar way. Light is the ripple, an electromagnetic disturbance, but the maximum speed of that ripple is encoded in the medium itself. The photon simply rides the properties of spacetime, following the fastest route allowed. This is why all observers, no matter how fast they move, measure the speed of light as the same. Spacetime adjusts to maintain consistency. If you accelerate, spacetime stretches or contracts around you so that the constant never breaks. Your measurement of time slows. Your experience of distance shrinks. These transformations are not illusions. They are the universe shifting to preserve the integrity of its structure. It may seem counterintuitive that spacetime can bend but still carry a strict limit. Yet this limit is precisely what makes bending possible. Light travels at one speed in vacuum, but when spacetime curves near a massive object, the direction and path light must follow warp. Gravity does not pull light the way it pulls objects of mass. Instead, it reshapes the geometry around light, guiding it along gently curved trajectories. The speed remains the same locally, but the path becomes longer or shorter depending on how spacetime bends. Einstein summarized this idea with a quiet elegance. Mass tells spacetime how to curve, and curvature tells matter how to move. But photons, with no mass of their own, do not resist this curvature. They do not need momentum to arc around a star or fall into the gravitational well of a galaxy cluster. They simply follow the geometry set before them. We see evidence of this everywhere. When astronomers observe gravitational lensing, the bending of starlight by massive galaxies, they are witnessing spacetime's structure in action. The light's speed stays constant, but the geometry it travels through is distorted. This is why light from a distant quasar can appear in 2 or even 4 different places in the night sky. The paths it takes are different, but the speed along each path never changes. Spacetime shapes the journey without ever altering the limit. To understand how deeply this limit is woven into reality, we can look at what happens when motion approaches the speed of light. The object doing the moving feels spacetime resist, not through friction, but through geometry. Time slows, energy requirements grow, the object's own perception of distance changes. These effects arise not because of mechanical constraints, but because motion itself is defined by how spacetime measures intervals. When your velocity increases, you begin to experience the fabric differently, like a swimmer sensing the currents change as they push through deeper waters. And if you could somehow continue accelerating, you would find the resistance grows without bound. The universe will not let you reach light speed because doing so would require your experience of time to stop entirely, an impossibility for anything with mass. Spacetime preserves this distinction with perfect consistency. Mass can curve spacetime, light can trace its shape, but nothing with mass can ever occupy the same relationship to time that a photon does. This brings us to one of the most beautiful insights of relativity. The speed of light is not just a limit on speed. It is a limit on how cause and effect can unfold. Information cannot travel faster than light because doing so would allow events to occur in contradictory orders. A cause could arrive after its effect. A signal could return before it was sent. Spacetime prevents these paradoxes by setting a maximum rate at which influences propagate. In this way, the speed of light functions as a guardian of cosmic coherence. It ensures that time flows in a direction that makes sense, that events unfold in sequences that can be understood. Without this constraint, the universe would be chaotic, impossible to navigate, impossible to describe. Even the simplest notion, one moment following another, would break. Deep within the mathematics of relativity lies an astonishing fact. The structure of spacetime emerges naturally from the requirement that information travel at a finite speed. If signals could propagate instantly, there would be no meaningful separation between locations. All events would be entangled in one undifferentiated moment. Space would collapse conceptually. Time would lose significance. It is precisely because the speed of light is finite that the universe can have size, shape, and duration. Yet, even though spacetime feels static to us, like a vast unmoving stage, it is anything but. It expands, it curves, it stretches across billions of light years, and every change in its shape influences the behavior of light. The cosmic microwave background, the faint afterglow of the Big Bang, still reaches us today because spacetime has expanded around it for nearly 14 billion years. Photons have traveled across this shifting fabric, faithful to its rules, tracing its evolution in their wavelengths. When astronomers use distant galaxies as markers to measure cosmic expansion, they are not measuring the galaxies themselves. They are measuring how the universe's fabric stretches the light those galaxies emit. The redshift of distant starlight is not a Doppler effect in the conventional sense. It is spacetime lengthening the wave as it expands. Light never slows. It never changes its intrinsic nature. But the medium it travels through evolves, and that evolution leaves fingerprints. If you could visualize this medium, if spacetime were illuminated for a moment, you would see a landscape of gentle curves, deep wells, vast plateaus, and expanding distances. Every star, planet, and galaxy bends it subtly. Every photon travels through its contours with perfect obedience. And beneath all these movements lies the same unwavering rule. Nothing outruns the maximum speed set by the fabric itself. As we drift deeper into this quiet story, one question naturally follows. If spacetime enforces the limit so carefully, what happens to things that carry mass as they attempt to approach it? Part 3. Why nothing with mass can reach light speed. At first glance, it seems simple. Things with mass accelerate slowly. But hidden beneath that simplicity is a deeper truth, that the closer something comes to light speed, the heavier its energy becomes, until motion itself demands infinite energy. In this section, we follow that quiet mathematical barrier to its source. To begin, imagine standing in a still field on a calm evening. The air around you is silent, the world unhurried. Now, imagine taking a single step forward. Nothing resists you except the ground beneath your feet. For everyday motion, this relationship remains intuitive. Push harder, move faster. But in the deeper language of physics, velocity is not just a measure of movement through space, it is a measure of how you move through spacetime itself. And spacetime hold strict rules for how mass behaves. At low speeds, Newton's simple laws work beautifully. Double the force, double the acceleration. But as an object's speed grows, especially when it reaches a significant fraction of the speed of light, those familiar rules begin to break down. The object's momentum does not merely increase proportionally. It grows in a way that steepens dramatically, like a hill that becomes steeper with every step. This steepness is not due to friction or air resistance. It arises from the fundamental geometry of spacetime. Einstein's special relativity tells us that an object's energy increases with velocity, following an equation whose curve rises sharply as it approaches light speed. This is often described as relativistic mass, though modern physicists prefer to say that the object's energy, not its mass in the usual sense, grows without bound. Still, the effect is the same. The closer the object gets to the cosmic limit, the harder spacetime pushes back. It is not a mechanical push, but a geometric one, woven into the mathematics itself. Imagine trying to push a boat toward the current of a powerful river. At slow speeds, the resistance is gentle, but as you try to match the river's speed, the resistance grows. Eventually, no amount of effort will allow you to equal the river's flow. Light speed is similar, but the resistance comes not from water, but from the very structure of reality. To understand this resistance, we can look at how time behaves. As speed increases, time slows for the moving object relative to an outside observer. This is not perception. It is not a trick of clocks. It is a real stretching of time itself. At 90% of the speed of light, time slows to about half. At 99.9%, it slows dramatically, almost freezing from the viewpoint of an external observer. Reaching the speed of light would require time to stop entirely for the traveler, an impossibility for anything with mass. Time cannot reach zero for massive objects, because time is one of the dimensions they move through. To halt it would be to halt existence in its current form. So the barrier is not simply energetic, it is also temporal. Motion at light speed belongs to massless particles, photons, gluons, gravitational waves, entities that do not experience time the way matter does. They have no rest frame. They never age. They exist in a state of perpetual motion because the geometry of spacetime allows them to, and only them. Another way to see the barrier is through length contraction. As you accelerate, distances in front of you shrink. At moderate speeds, this effect is tiny, imperceptible. But as you approach light speed, the contraction becomes extraordinary. The universe ahead seems compressed into a narrow corridor of space. If you were to reach the speed of light, the distance in front of you would contract to zero. The entire universe would collapse into a single point along your line of travel. For something with mass, something that occupies space, this collapse cannot occur. Mass requires volume. Volume requires a meaningful measure of distance. Light, which has no rest mass, slips through this loophole perfectly. Matter cannot. These shifts in time and space do not occur to punish motion. They occur to protect coherence. They ensure that causality, events happening in an order that makes sense, is preserved. If an object with mass could exceed light speed, it could theoretically arrive at a destination before it departed. Signals could loop backward in time. Causes could follow effects. The universe prevents these paradoxes by enforcing the boundary elegantly, through geometry rather than force. And yet, even as the barrier stands firm, it remains tempting to ask, what if we simply add more energy? Could we brute force our way to light speed? The answer lies in the energy curve of relativity. When an object is at rest, it has rest energy, described by the famous equation E in mc2. As it moves faster, its energy grows. At 10% light speed, the increase is modest. At 50%, it becomes noticeable. At 90%, the energy required for each additional percentage of speed skyrockets. By 99.9999%, the energy required becomes so vast it rivals the output of stars. To reach 100% would require infinite energy, and infinite energy is not available in a finite cosmos. Particle accelerators illustrate this perfectly. Devices like CERN's Large Hadron Collider can push protons to 99.999% of the speed of light. At these speeds, the protons carry energies thousands of times their rest mass. Yet no matter how powerful the accelerator becomes, it cannot push the proton to the true limit. It can only approach, never touch. The closer it gets, the more energy pours into the attempt, with diminishing returns. Even nature's own accelerators, supernovae, magnetars, active galactic nuclei, cannot push particles beyond the threshold. Cosmic rays, the fastest particles ever observed, come astonishingly close. Some have energies so immense that a single particle carries as much kinetic energy as a thrown baseball. But even these particles, traveling for millions or billions of years, never cross the boundary. They race through spacetime at speeds so close to light that from their perspective, they traverse galaxies in moments. But they remain sublight. Always. Even hypothetical technologies, warp drives, wormholes, spacetime shortcuts, do not violate this rule. The geometry can be manipulated, but the local speed of matter through space remains bounded. These concepts do not accelerate objects faster than light. Instead, they bend spacetime around them, preserving the cosmic limit. The more deeply we look, the clearer the reason becomes. The speed of light is not a speed at all in the usual sense. It is the scaling factor of spacetime. It is the conversion ratio between space and time, the number that tells the universe how to balance distance against duration. Asking a massive object to reach light speed is like asking a shadow to outrun the object casting it. The relationship defines the limit, and within this quiet barrier lies a profound symmetry. Light travels at the speed it does because it has no mass. Mass cannot reach that speed because it requires time to flow. Time cannot stop for matter, and matter cannot slip free from its own inertia. The universe keeps these categories distinct to preserve the clarity of cause and effect. This separation, massless and massive, timeless and time-bound, is one of nature's most elegant distinctions. So the next time you imagine a spacecraft racing through the galaxy, remember this. It is not technological failure that prevents light-speed travel. It is the geometry of the universe itself, a structure built not to confine curiosity, but to preserve order. And as we continue this quiet journey, another question rises gently from the horizon. If reaching the speed of light is impossible for mass, what does the universe reveal when we merely approach it? Part 4. Time's gentle shift. How time slows as you move faster. Imagine taking a single step and experiencing time passing a little differently than someone standing still. This isn't imagination, it's physics. As motion increases, time dilates, stretching softly, changing tempo, revealing why light speed is not just a limitation of motion, but of time itself. To understand this quiet transformation, we must first release the idea that time flows the same for everyone. For most of human history, time felt universal, each second identical, each minute the same length, whether experienced by a traveler or a shepherd, a thinker or a wanderer. But in the early 20th century, Einstein showed that this intuition is only an approximation. Time is not a river running steadily through the universe. It is woven into motion itself, changing shape as speed increases. Imagine two clocks. One rests gently on a table, the other is carried forward at a noticeable fraction of the speed of light. Though they may be identical in their construction, they will not agree. The traveling clock will tick more slowly than the one left behind. Not because it has malfunctioned, and not because its gears have worn differently, but because time for that clock, its own proper time, has simply passed more slowly. This effect, known as time dilation, is one of the most tested and confirmed predictions in physics. It arises naturally from the structure of spacetime. The faster the clock moves, the more spacetime bends the flow of its time. At speeds familiar to us, walking, driving, even flying, this effect is too small to notice. But as one approaches significant percentages of the speed of light, the stretching becomes dramatic. Consider a spacecraft traveling at 90% light speed. For every hour the traveler experiences, more than 2 hours pass on Earth. At 99%, the ratio grows more astonishing. At 99.99999%, time hardly moves at all for the traveler compared to an observer at rest. Time for them becomes a thin thread, narrowing as velocity climbs. This is not a metaphor. It is not an optical illusion. It is the actual tempo of time changing. To see why, imagine spacetime as a vast landscape, one where each possible path an object can take is shaped by how fast it moves. Motion bends this path slightly, altering the amount of time the object experiences along it. The faster it travels through space, the less time it can travel through. Speed and time are bound together in a delicate equation. Increase one, and the other must shrink. This relationship is encoded in the Lorentz factor, a mathematical expression that tells us exactly how time stretches as motion grows. But beyond the symbols, the meaning is deeply intuitive. The universe maintains a balance. If an object moves through space with great swiftness, it has less capacity to move through time. The two are not independent. They are different directions within the same fabric. We see this even in the smallest scales. Muons, short-lived particles created when cosmic rays strike Earth's atmosphere, should decay almost instantly. Their natural lifetime is too short for most of them to reach the planet's surface. And yet, billions of muons pass through your body each second, their clocks slowed by their tremendous speed. Time dilation allows them to survive their journey long enough to be detected. These tiny particles become messengers, carrying confirmation that time's flow depends on motion. This same effect must be corrected for in the GPS satellites orbiting Earth. Their clocks tick slightly faster because they are farther from the planet's gravity, yet also slightly slower because of their high speed. Engineers must apply Einstein's equations daily to ensure that your phone knows where you are with precision. Without accounting for time dilation, GPS locations would drift kilometers each day. Even everyday technology depends on the malleability of time. But time dilation becomes most profound when approached from a human perspective. Imagine an astronaut embarking on a journey to a star system many light years away. If she could accelerate to near light speed, the passage of time aboard her ship would slow dramatically. A journey that feels like a handful of years to her could correspond to decades or even centuries on Earth. When she returns, the planet she left behind may have aged far beyond her own experience. This possibility, known as relativistic time. Travel does not require paradoxes or fictional devices. It emerges directly from the geometry of space-time. By moving quickly, she would simply experience less time. Her body would age more slowly. Her cells would divide at a slightly slower rhythm. Her life would follow a different timeline than the world she left. Stephen Hawking once remarked that the future is open to us, waiting in precisely this way. If we move fast enough, time will gently bend to accommodate our journey. It is only the past that remains inaccessible, but the future can be reached in fewer years of one's own time if one travels swiftly enough through space. The key insight is that time is not absolute. It does not tick universally across the cosmos. It is not a single rhythm keeping pace with the stars. It flows differently depending on motion and gravity, bending in response to the energy around it. From this perspective, the speed of light becomes more than a limit. It becomes the boundary at which time behaves in its most extreme form. A photon, massless and always traveling at the cosmic maximum, experiences no time at all. From its viewpoint, if such a viewpoint could exist, its entire journey from the core of a star to the eye of an observer would be instantaneous. Time for a photon does not flow. It does not age. It does not exist in the same temporal sense that matter does. This contrast reveals why mass cannot reach light speed. To do so would require time to halt entirely for the traveler. Every heartbeat, every chemical reaction, every vibration of every atom would freeze. Time must remain positive for anything that possesses mass, and so the universe protects its structure by preventing such an interruption. The beauty of time dilation is that it never announces itself harshly. It does not break continuity or disrupt experience. For the traveler moving quickly, nothing feels unusual. Their heartbeat remains steady. Their thoughts unfold naturally. They feel time passing at its normal pace. Only the perspective of an observer in a different frame reveals the change. Two people, moving differently through space, live through different amounts of time, yet both feel their own experience as smooth and natural. Relativity does not distort personal experience. It aligns each person with their own proper time, honoring the continuity of consciousness even as the universe bends around them. This softness is what makes time dilation so strangely peaceful. It is not a violent tearing or a sudden shift. It is a gentle stretching, like a fabric responding to pressure, and it preserves coherence with exquisite care. No matter how the universe curves or how fast we move within it, causality remains intact. Events unfold in an order that each observer can understand, even if their sequences differ. So as you imagine motion through the cosmos, as you imagine a ship gliding between stars or particles racing through space, remember that time itself is not fixed. It is flexible, responsive, alive to the dynamics of movement. And as we drift deeper into this journey, one quiet question arises. If time itself stretches under speed, what begins to happen when we push motion closer and closer to the cosmic limit? Part 5. The horizon of speed. What happens at 99.9999% of light speed? When you approach the speed of light, the familiar world begins to distort. Length collapses, time stretches, energy grows. In this segment, we drift toward that boundary, never crossing it, but watching its effects become unmistakably real. To understand the horizon of speed, imagine sitting inside a spacecraft designed not just for travel, but for an experiment in perspective. At rest, the cabin feels ordinary. The hum of instruments is steady, the stars outside seem scattered in quiet patterns, and time passes with its usual soft rhythm. But as the vessel accelerates, something subtle begins to unfold, not outside, but in the deep mathematical language of spacetime surrounding you. At first, you feel nothing unusual. As countless astronauts have said, steady velocity reveals no sensation. But as you approach significant fractions of light speed, 90%, 95%, 99%, the equations governing motion begin to fold and transform. The laws do not break. They reshape themselves to preserve consistency. And your experience, though silent and smooth, begins to shift. Let us begin with length contraction, one of the most counterintuitive consequences of relativity. As your speed increases, distances along the direction of travel grow shorter. Not only the space outside the ship, but even the ship's own structure, as measured by an outside observer, shrinks. If the craft is 100 meters long at rest at 99.999% light speed, it may appear to external observers as only a few meters. The ship does not crumble. It does not compress physically. Instead, space-time changes the way distances are measured for objects in motion. From your perspective inside the vessel, nothing is different. The floor remains the same length. The walls stand where they always have. But the universe outside is another story. Stars ahead of you seem closer than they should be, as though the corridor of space you are traveling through has contracted. This is not an illusion of optics. It is geometry bending around velocity. Next comes time dilation, the quiet slowing of your personal clock relative to the universe you leave behind. Even at 90% of the speed of light, time for you flows at less than half its normal rate for someone stationary. Push closer to the horizon of speed, to 99.9999%, and the effect becomes dramatic. A single hour aboard the craft may correspond to days, weeks, or more in the world outside. If you were to complete a journey lasting only a few years of your own life, centuries could pass on Earth. Again, from within the ship, you feel no distortion. Time flows naturally. Each second appears normal. But relativity guarantees that your timeline diverges from the timeline of others. It is not a distortion of memory or a trick of perception. It is a reshaping of the space-time interval you travel along. While length contracts and time dilates, a third transformation emerges, one tied intimately to energy. As your speed increases, your kinetic energy grows not linearly, but exponentially. If you double your speed near light speed, the energy required may increase by factors of thousands. At 99.9999%, the energy needed to push further begins to rival that of stellar processes. The vessel's engines strain against a barrier not built of matter, but of mathematics. This is why light speed cannot be reached, not because of resistance in the traditional sense, but because approaching it demands energy without bounds. The universe gently but firmly maintains this divide, preventing any massive object from crossing the boundary that separates time-bound matter from the timeless motion of light. As speed increases further, another extraordinary phenomenon reveals itself: relativistic beaming. Light ahead of you concentrates into a narrower and narrower cone, as though the universe is pouring itself into a tunnel of brightness straight ahead. Stars directly in front of you intensify. Their light shifts toward the blue end of the spectrum due to Doppler effects, while stars behind you fade, their light stretched into infrared wavelengths your eyes cannot see. The forward sky becomes a bright, compressed halo. The rear sky grows darker, quieter, more distant. Direction itself becomes distorted by speed, guiding your perspective toward the horizon you approach but cannot cross. Beyond the change in light, there is relativistic aberration, a gentle but unmistakable shift in how angles work. Objects that once appeared to your side or slightly above seem to slide forward, as though all of existence is being pulled toward your line of travel. The universe appears to rearrange itself into a tighter field of vision. As we drift further toward the boundary, past 99.99%, past 99.999%, the very texture of radiation changes. Cosmic microwave background photons, normally harmless, increase in energy as your speed blue shifts them. Eventually, if you were moving fast enough relative to this background, even the faint afterglow of the Big Bang would appear as intense radiation. This is not a catastrophic limit, but another reminder. The universe is designed so that extreme motion carries consequences. Meanwhile, particles of dust and gas, ordinarily insignificant, become dangerous at these speeds. Even a grain smaller than a speck of sand encountered head-on at 99.9999% light speed would carry energy comparable to an explosive. The vacuum of space, so empty at rest, becomes a sea of energetic collisions when approached at near-light motion. Yet, for all these challenges, the experience inside the ship remains calm. Your body does not feel the compression of space or the slowing of time. Your thoughts unfold naturally. The hum of the engines beats softly, steady as a heartbeat. Only instruments reveal the truth, clocks diverging, distances transforming, energies rising without bound. One of the most profound effects at this horizon is the shift in simultaneity. Events that appear simultaneous to you no longer appear simultaneous to those watching from afar. Two flashes of light that seem to occur at the same moment in your cabin will be seen unfolding at different times by distant observers. This difference is not due to delay or distance. It is woven into how spacetime reorganizes its coordinates for observers in motion. Near light speed, simultaneity becomes relative, fluid, rearranged by velocity. And yet, the laws of physics remain consistent. Observers inside and outside the craft each experience a coherent world. Their timelines unfold smoothly. Their causal sequences remain intact. Relativity ensures that no contradictions arise. It allows reality to stretch and tilt without breaking. At 99.999% of light speed, everything we understand about motion reaches its most poetic boundary. You feel still, yet the universe rushes past. Your time flows gently, yet cosmic epics may be unfolding outside. Distances shorten, yet energy expands. Light concentrates into a forward cone, yet the darkness behind grows deeper. Here, in this threshold region, the nature of spacetime reveals itself with striking clarity. The speed of light is not a wall you smash into. It is a horizon you approach with infinite effort, a horizon that reshapes everything around it to protect the coherence of the cosmos. And as you drift just beneath this limit, close enough to sense its structure but never to touch it, a final question rises softly from the fabric of spacetime. If this is what happens as we near the limit, what happens to the particles that live at the limit permanently, those that experience no time at all? Part 6. Why light needs no time, photons and the view from the limit. A photon experiences something strange. To us, it travels for billions of years across the universe. But from the photon's perspective, no time passes at all. Here, we explore the quiet paradox of a particle that never stops moving and never experiences a journey. To understand this contradiction, we must begin by remembering that time is not universal. It does not tick the same way for every observer. Time is tied to motion, particularly to how an object moves through spacetime. An object that moves slowly through space experiences time at its normal rhythm. But as motion increases, the flow of time slows. At the speed of light, time itself comes to a halt. For anything with mass, atoms, dust, planets, people, reaching this boundary is impossible. But for a photon, it is simply the default. A photon is born at the cosmic limit and remains there every moment of its existence. It never accelerates to the speed of light. It does not need to. It emerges into the universe, traveling at that speed because the laws of physics leave it no other option. A photon has no rest mass, and without mass, it has no rest frame. It can never be at rest. It can never pause. It exists only in motion. This absence of rest changes how time unfolds for a photon. When we speak of a photon's perspective, we step into metaphor because relativity tells us such a perspective cannot truly exist. If time does not pass for a photon, then it cannot experience a sequence of events. It cannot have a before or an after. It cannot experience distance. It cannot perceive the journey it makes across the cosmos. And yet, from our vantage point, from the slow, time-bound rhythms of matter, a photon's path is astonishing. Light leaving a star in a distant galaxy may travel for 13 billion years before reaching the mirror of a telescope. During that time, galaxies collide, stars are born, planets form, life arises, civilizations awaken and fade. Entire epochs pass. But for the photon itself, not a single moment elapses. The journey is instantaneous. This is the first deep paradox. Time stretches infinitely for an observer moving at light speed, but collapses entirely for the light itself. To see why, imagine spacetime as a vast grid. Each object moves through both space and time along a path called its world line. For massive objects, the world line leans through spacetime in a way that includes both space-like and time-like components. But for a photon, the world line becomes a perfect diagonal across the grid. Pure motion, no rest, no passage of time. In the mathematics of relativity, this special path is called a null geodesic. Along such a path, the interval of spacetime, what we would interpret as proper time, equals 0. In other words, if a photon could carry a clock, that clock would never tick. Every second that passes for us corresponds to no time at all for the photon. Because of this, the concept of aging does not apply to light. The photon you see from the Big Bang, the faint whisper of radiation that became the cosmic microwave background, has existed for nearly the entire life of the universe. Yet for the photon, the moment it left that early plasma and the moment it touched a detector here on Earth are separated by no internal experience whatsoever. It was born. It arrived, with no sense of an interval in between. As strange as this seems, the universe gives us many clues that confirm it. Take the phenomenon of redshift. When the universe expands, the wavelength of distant starlight stretches. The photon's energy changes. But even as it journeys across an expanding cosmos, it has no awareness of the distance it covers. The shifting wavelength is not something the photon experiences. It is something we observe as we measure its arrival after eons of cosmic growth. Or consider gravitational lensing. A photon traveling near a massive galaxy may have its path bent by gravity. From our perspective, we see light curve, split, or magnify around objects. But for the photon, this curve is not a detour. It is the path spacetime provides. There is no turning, no decision, no resistance. The photon simply follows the geometry laid before it. Its journey has no intermediate states. Only emission and absorption. There is another subtle truth hidden here. A photon does not occupy space in the way matter does. It has no volume, no internal structure, no boundary that persists through time. It is a ripple in an electromagnetic field, an excitation that moves with perfect fidelity to the fabric of spacetime. Without the passage of time, a photon cannot store memories or perceive motion. It cannot look back. It cannot anticipate. It is a transient pattern that only exists in the moment it is interacting. And yet, this lack of temporal experience does not diminish its role. Photons are the carriers of information across the cosmos. They bring us the colors of stars, the afterglow of cosmic dawn, the signatures of atoms in distant nebulae. They encode the history of galaxies. They trace the imprint of gravitational waves. Light is the universe's messenger, yet the messenger never feels the journey. To us, this raises a profound question. If a photon experiences no time, can it be said to exist between emission and absorption? Einstein himself hinted that this question might be ill-posed. In relativity, between is a temporal concept, meaningful only for observers who experience time. The photon does not. For the photon, the universe has only two events, the moment it emerges and the moment it is absorbed. The entire vast distance between star and eye collapses into a single mathematical link, a connection without duration. This leads to a second paradox. Photons mediate forces and carry energy, yet they do not experience motion. They possess momentum without mass. They deliver pressure without touching. They change the energy states of atoms without ever having lived through the interval between those atoms. The closer we look, the more the photon becomes a bridge between spacetime events, between places in the cosmos, between the past and the present, without occupying any of those places in the way we understand. Some physicists describe the photon not as a particle traveling through space, but as a transfer of energy and momentum encoded in the structure of the electromagnetic field. Under this view, the photon's travel is a story we tell within our human framework of time. In the deeper mathematics of the universe, the journey is simply the unfolding of field interactions across spacetime. And yet, the poetic truth remains. From our perspective, the photon has traveled. It has crossed gulfs so immense that even imagination strains to span them. It has brought us light from the dawn of creation. It has given us insight into the nature of stars, galaxies, and the universe itself. But from the photon's own frame, a frame that does not truly exist, there is no dawn, no crossing, no arrival, only a single moment infinitely extended. This contrast between the time-bound world we inhabit and the timeless existence of light is one of the quiet wonders of relativity. It reveals how richly layered the universe is, how different observers can inhabit realities that are equally valid, yet profoundly different. And as we let this idea settle, a new question flickers at the edge of our curiosity. If light experiences no time, then how does it define the very measurements of space and time we rely on, from rulers to clocks, from the beat of a second to the depth of the cosmos? Part 7. The universe's speedometer, how light defines space and time. Our rulers measure distance, but those rulers only make sense because light behaves predictably. Our clocks measure time, but they tick because light oscillates in patterns that never falter. In this chapter, we uncover how the speed of light silently shapes every measurement we use. When you hold a ruler in your hand, it seems like a solid, objective thing. Its markings appear permanent, stable, carved into the surface. But beneath that familiarity lies a subtle truth. A meter is not defined by a physical stick, nor by the length of a metal bar stored in a laboratory vault. Instead, a meter is the distance light travels in a tiny fraction of a second, specifically 1,297,458 of a second. This means that every time you measure length in the modern world, you are measuring the behavior of light. Our sense of distance is anchored in the cosmic speed limit. This idea may feel strange at first, but it arose from necessity. Early rulers, no matter how carefully crafted, suffered from imperfections. Temperature changes made them expand or contract. Tiny mechanical stresses could distort their shape. Even humidity could cause small deviations. Physicists eventually realized that to define distance reliably, they needed something that never changed. light became the perfect candidate. Its speed in a vacuum is constant, unwavering, and universal. No matter where you are or how fast you're moving, if you measure the speed of light, you will always get the same number. So scientists inverted the relationship. Instead of using rulers to measure the speed of light, they used the speed of light to define the rulers themselves. In this way, light became the universe's quiet measuring stick. The same is true of time. Atomic clocks, the most precise instruments ever built, function by measuring the frequency at which electrons jump between energy levels in atoms. These jumps release or absorb light at exact, repeatable wavelengths. That frequency becomes the beat of the clock. 1 second is defined as 992,631 oscillations of the light emitted by a cesium atom. This number is not arbitrary. It is grounded in how atoms behave, how light emerges from them, and how stable these oscillations remain across the cosmos. Every modern measure of time is tied to the rhythm of light. This deep relationship reveals something profound. We do not measure space and time by themselves. We measure how light moves through them. Distance is how far light travels. Duration is how many times light oscillates. Even the shapes of our units, meters, seconds, are shadows cast by the properties of radiation. And because light speed is woven into the geometry of spacetime, these measurements remain consistent irrespective of who measures them. Whether you are in a laboratory on Earth, orbiting the planet on the International Space Station, or traveling between planets, the fundamental definition remains unchanged. This consistency becomes even more significant once we consider relativity. In Einstein's view, spacetime is not a rigid grid but a flexible fabric. Distances and durations change depending on motion and gravity. A moving observer experiences shorter lengths. A clock near a massive object ticks more slowly than one far from it. These variations could have made measurement chaotic, if not for the constancy of light. Light stabilizes measurement in a dynamic universe. When astronauts aboard satellites compare their clocks to those on Earth, corrections must be made for both gravitational time dilation and motion-induced time dilation. GPS satellites in particular must account for these changes every single day. Without these adjustments, the navigation system would drift by kilometers within hours. But because light's oscillations remain consistent, engineers can reconcile distortions and preserve accuracy. Light becomes the reference frame that ties together shifting perspectives. This becomes even more essential at cosmic scales. Astronomers measure the distances to distant galaxies not with rulers, but with light itself. They use standard candles, stars with known brightness, and observe how their light dims over distance. They measure redshift, the stretching of light waves as the universe expands. They track the arrival times of photons emitted billions of years ago. Every insight we have about the size, shape, and age of the universe arises from how light behaves. Even the expansion rate of the universe, the Hubble constant, is derived from light traveling across immense stretches of space-time. Without light as a universal messenger, the cosmos would be a silent, unknowable expanse. Another layer of this story emerges when we consider the symmetries of the universe. The laws of physics must remain consistent across all frames of reference for nature to make sense. Light plays a central role here. The fact that all observers measure the same speed of light forces space and time to adjust themselves depending on motion. This interplay ensures that two observers, even if they are moving relative to each other, will agree on the fundamental equations that govern reality. The universe bends time and space to protect the constancy of light. This may seem counterintuitive, but it is the backbone of relativity. If someone moves past you at high velocity, they may measure the distance between 2 points as shorter than you do. They may measure the duration between two events as different from your measurement. Yet both of you will measure the speed of light as exactly the same. To preserve this symmetry, space-time itself reshapes around motion. Without the fixed speed of light, these symmetries would crumble. The laws of physics would differ depending on one's speed or direction. The universe would lack coherence. It is the unchanging speed of light that keeps the cosmos mathematically harmonious. But there is something even more elegant beneath these ideas. Because the speed of light links space and time, it acts as a kind of conversion factor. It tells the universe how much space equals how much time. In equations of relativity, distances and durations can be translated into one another using the speed of light as the bridge. Space becomes time multiplied by light speed. Time becomes space divided by light speed. The entire structure of spacetime hangs upon this relationship. Without light, we would not be able to connect the two dimensions. Without this connection, there would be no unified spacetime. Light is the thread that weaves them into a single tapestry. And so, even though we think of light as something that illuminates our world, its deeper role is far more fundamental. Light defines our rulers. Light defines our clocks. Light defines the geometry of the universe. Without it, there would be no coherent way to measure reality. Light is the universe's silent speedometer, the benchmark by which all motion, distance, and time are judged. And as this truth settles gently around us, another question begins to take shape in the quiet. If the speed of light anchors space and time so firmly, what happens when particles seem to outrun light, at least within certain materials, without ever breaking the cosmic limit at all? Part 8. Breaking the limit without breaking physics. Tachyons and hypothetical faster than light. Particles. For decades, physicists have wondered whether particles might exist beyond the cosmic speed limit. If they do, they must obey entirely different rules, moving faster than light but never crossing below it. Tonight, we explore these hypothetical beings known as tachyons and why they remain mathematical shadows. To approach this idea, we must begin with a simple but startling truth. The speed of light is a boundary, but relativity never claimed that nothing could exist on the far side of it. What relativity tells us is that nothing with mass can reach or exceed the speed of light from below. But it does not forbid the possibility that something might begin its existence already beyond that limit, forever out of reach from our side of the boundary, living in a realm where motion itself behaves differently. That possibility led physicists to theorize about particles called tachyons. Their name comes from the Greek word tachys, meaning swift. In theory, a tachyon would never slow down to the speed of light, just as no ordinary particle can ever speed up to it. The barrier works both ways. For us, beings made of matter that experiences time, the speed of light is a ceiling. For a tachyon, that same speed would be a floor, unreachable from above. If tachyons existed, they would travel faster than light not by violating relativity, but by living on the opposite side of its equations. To understand this, imagine the speed of light as a kind of shoreline. All familiar particles, electrons, protons, atoms, planets, you, move on the landward side of that boundary. No matter how fast you run, you cannot cross the water's edge because the geometry of spacetime resists your approach. A photon, massless and forever racing at the limit, skims the boundary precisely. A tachyon, however, would swim in the open ocean beyond that shoreline, never touching land, never slowing enough to cross into our domain. It would live in a region of spacetime where distances and times behave in inverted ways, where motion through space outruns any exchange of signals between familiar objects. This reversal creates fascinating consequences. A tachyon's energy, according to special relativity, would behave in the opposite manner from normal matter. For us, as speed increases, energy increases. For tachyons, the mathematics suggests the reverse. A tachyon with infinite speed would carry zero energy, and a tachyon with speeds just above light speed would require enormous energy. In other words, the faster a tachyon goes, the less energy it has. This inversion is not a contradiction. It is simply the mirror image of our own constraints. Yet, as beautiful as the mathematics may be, tachyons bring with them a profound challenge. They appear to break causality. If something moves faster than light, then in certain frames of reference, it could appear to travel backward in time. An effect could precede its cause. A signal could arrive before it was sent. In relativity, this creates time loops and paradoxes with no clear resolution. To preserve the integrity of spacetime, physics would need some mechanism that prevents tachyons from interacting in ways that violate causality. or restricts the frames from which they can be meaningfully described. Some theories attempt exactly this. In certain quantum field theories, tachyons do not represent literal faster-than-light particles. Instead, they signal an instability in the vacuum, a state where the field wants to roll to a lower energy configuration. In these interpretations, tachyons are not physical matter, but mathematical cues that a system will evolve. The Higgs mechanism famously contains such a tachyonic mass term before symmetry breaking occurs. In this context, the word tachyon does not imply faster-than-light behavior, but a field waiting to settle into a stable form. Other theories take tachyons more literally. If tachyons truly traveled faster than light, their interactions might be constrained so tightly that they could never send usable information back in time. They might exist, but remain unable to communicate across the boundary in a way that introduces paradox. They could inhabit a separate region of spacetime, reachable only through equations, never through experiment. This distinction highlights something important. Tachyons are theoretical, not because they contradict relativity, but because no experiment has ever detected them. They remain mathematical solutions of equations rather than residents of the universe we observe. Still, the idea captivates the imagination, because tachyons challenge us to examine what speed limits truly mean. The cosmic speed limit is not a wall, but a division between two kinds of existence. On our side, time flows forward, and motion remains subliminal. On the far side, time's meaning is altered, and motion transcends the categories we rely upon. For example, if a tachyon existed, its world line, the path it traces through spacetime, would be unlike ours. Ordinary matter traces time-like paths, always moving forward in time as it moves through space. Light traces null paths, experiencing no time at all. A tachyon would trace a space-like path, where its motion through space outpaces any potential motion through time. Whether such a world line could physically exist is unknown. The mathematics allows it, but nature often chooses solutions that mathematics does not. Tachyons sit at the boundary between the allowed and the realized. Perhaps the most intriguing aspect is this. If tachyons existed, we might never be able to detect them directly. Any attempt to slow them to the speed of light would require infinite energy, just as accelerating us to light speed would require infinite energy. The boundary protects both sides. The two worlds remain forever separated by the same cosmic law. This leads to a final, quiet possibility. Tachyons may exist, but not for us. They may populate regions of spacetime in ways we cannot observe or influence. They may drift across dimensions predicted by string theory. They may serve as mathematical placeholders for instabilities or transitions within quantum fields. Or they may not exist at all, their elegance confined to chalkboards and equations. Either way, they teach us something profound about the structure of the universe. They remind us that the speed of light is not merely a velocity, but a threshold that divides reality into domains, time-bound, timeless, and hypothetically superluminal. They reveal how deeply motion, time, and energy are tied together. And they show that even imaginary particles can illuminate real features of the laws that govern our world. As we drift away from these hypothetical beings, these swift shadows that may or may not inhabit the far side of physics, another question emerges quietly. From the boundary they guard, if particles cannot communicate faster than light, how does the universe ensure that information itself never outruns the cosmic limit? Part 9. The Cosmic Speed Trap. Why information can never outrun light. A message, a signal, a cause. None of these can exceed the speed of light without unraveling the structure of causality itself. Here we explore why information is bound to this maximum and how the universe preserves the order of events by guarding this limit. To sense the depth of this law, imagine striking a match in a dark room. The spark, the flare, the warm color spreading outward. These are all forms of information carried by light. They tell the walls, the objects, and your own eyes that something has happened. Now, imagine whispering into the air. The sound travels slower, carried by vibrations of molecules. But beneath that, and beneath every kind of signal in the universe lies a deeper structure. Information cannot spread faster than the geometry of spacetime permits, and the maximum speed of that propagation, the ultimate communication rate allowed by nature, is the speed of light in a vacuum. This rule is not arbitrary. It is woven into the structure of reality. If information were to travel faster than light, signals could leap across time in ways that defy order. A cause might arrive after its effect. A message sent could return before it left. The sequence of events, the very fabric that allows the universe to make sense, would collapse into paradox. To understand why, we must explore the connection between speed, time, and reference frames. In relativity, there is no universal now. What counts as simultaneous depends on the observer's motion. Two events that appear to happen at the same time for one observer may unfold in a different order for someone moving at a high speed relative to them. This relativity of simultaneity is subtle, quiet, and completely invisible in everyday life, but it becomes crucial when imagining faster-than-light communication. Suppose you could send a signal faster than light. In your own frame, this might seem harmless. You send the message, and it arrives instantly. But in another observer's frame, one who is moving at a significant fraction of light speed, the same signal could appear to arrive before you sent it. That observer could then send a reply, also faster than light, which might return to you before you initiated the entire exchange. You would receive the reply before you asked the question. A paradox is born. The universe has no mechanism to resolve a contradiction like this. The simplest solution is the one nature chooses: forbid faster-than-light information transfer. This is why the cosmic speed limit is not only a law about motion, it is a law about logic. The structure of spacetime contains light cones, geometric shapes that determine what events can influence each other. Every event you experience exists at the tip of its own cone. Inside the cone are all points that can be reached by signals traveling at or below light speed. Outside the cone are points that cannot influence or be influenced without breaking causal order. Nothing meaningful crosses the boundary between these regions faster than light. Light defines the causal horizon, the boundary of influence. This is why the universe preserves the direction of time. If you cannot send a signal outside your light cone, you cannot communicate with your own past. Time keeps its steady, unbroken flow because nothing can disturb the order of cause and effect. Even gravity respects this limit. In Newton's time, gravity was imagined as instantaneous, a force acting across distance without delay. But relativity corrected this. Changes in gravitational fields travel at the speed of light. When two black holes collide, the ripples they produce, gravitational waves, expand outward with a speed identical to light. If the sun were to vanish suddenly, Earth would continue orbiting the empty space for about 8 minutes. Only then would the loss of gravity reach us. The universe whispers its changes at one universal pace. This cosmic rule extends to quantum physics as well. Consider quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. Two particles, once entangled, behave as if linked even across vast distances. Measure one, and the other seems to respond instantly. But despite appearances, no usable information travels faster than light. Entanglement correlations cannot be controlled. You cannot choose the outcome of your measurement in a way that sends a signal. The universe protects causality even when its behaviors appear surreal. In the subatomic world, the speed limit still holds firm. Another layer emerges in fields and forces. Electromagnetic interactions, which govern light, electricity, and magnetism, propagate at light speed. The strong and weak nuclear forces operate only over tiny distances, but even their interactions respect local propagation limits tied to the speed of light. Communication is not just matter exchanging particles, it is information encoded in forces, and every force in nature respects the same ultimate ceiling. But what about fields that appear to change instantly? In classical physics, electric fields seem to adjust instantly when charges move. In reality, it is the static approximation of a deeper truth. the changes propagate outward at light speed. Our equations merely hide the delay when distances are small. The universe never allows physical information to teleport. Even the vacuum obeys the rule. When a charged particle accelerates, it emits radiation. That radiation carries information about the particle's motion, but only outward at the speed of light. The vacuum becomes a messenger of energy and momentum, but never a faster one. Why is the cosmic speed limit so rigid? One reason lies in the structure of spacetime, intervals. In Einstein's formulation, events are separated by distances in both space and time. These intervals determine whether information can flow between them. For ordinary matter, movement through spacetime follows time-like paths, always slower than light. For photons, the path is null, right at the boundary. Anything faster would require the interval to become space-like, and information in that regime could violate causal order. Thus, the speed trap is not a barrier, but a region of spacetime geometry. Information moving slower than light remains within the causal fabric. Information at light speed rides the boundary. Anything faster would fall outside the fabric altogether, unmoored from the rules that give the universe coherence. Even when physicists imagine ways around the limit, wormholes, warped spacetime, shortcuts, these mechanisms do not accelerate matter or information through space faster than light. Instead, they reshape the geometry so that distances themselves become shorter. The cosmic speed limit remains unbroken. Only the path changes, and that reveals the true power of this rule. It is not just about speed. It is the foundation of reality's consistency. It ensures that the universe has a past, present, and future that unfold in an order that can be known and understood. The more deeply we study the cosmos, the more we discover that this limit is not restrictive. It is protective. It preserves meaning. It preserves sequence. It preserves the delicate architecture of time. Without it, the universe might still exist, but it would not be a place where stories unfold, where causes shape effects, where moments follow one another with quiet certainty. And as we drift forward, guided by this universal boundary, another question gently emerges. If information cannot outrun light, what happens when we try to push objects themselves toward extreme acceleration? Where does the resistance come from, and how does spacetime respond when we press against its limits? Part 10. Spacetime under stress. What happens when you try to accelerate too fast? Push something harder, and for a brief moment, spacetime pushes back. Energy curves, geometry, motion drags time, and acceleration becomes a negotiation between mass and the universe's deepest laws. This segment reveals how acceleration itself becomes constrained as speed grows. To understand this quiet negotiation, imagine sitting in a spacecraft drifting in the calm of space. At rest, the universe feels open, stars scattered across the sky, silence stretching in every direction. But the moment you fire the engines, you stir the fabric of space-time itself. Acceleration is not merely a change in speed, it is a change in how you move through time. It reorients your path in space-time, bending your trajectory through a dimension that is both familiar and endlessly mysterious. At first, the response feels familiar. The engine's thrust pushes you back into your seat. Your body presses against the padding. Each moment of acceleration takes energy from fuel and turns it into motion. In these early stages, Newton's equations approximate the experience well. Double the thrust, double the acceleration. But beneath the familiar sensations, relativity is already quietly shaping your movement. Acceleration does not occur in a vacuum of laws. It occurs within the geometry of spacetime, and that geometry responds to energy. As your engine works harder, pumping more energy into your motion, spacetime adjusts. Time begins to slow for you relative to someone who remains still. Your own clocks tick normally from your perspective, yet outside, clocks begin drifting ahead. This is not a distortion in your instruments. It is the universe keeping its equations consistent. The faster you move, the more dramatic this drift becomes. Acceleration and time dilation are not separate effects. They are facets of the same structure. Motion through space bends time, and motion through time responds by stretching space. This interplay becomes most pronounced when your velocity begins to approach relativistic speeds. At 30% the speed of light, time dilation is present but gentle. At 80%, it becomes impossible to ignore. Your acceleration still produces increases in speed, but each burst of thrust yields less additional velocity than the last. You are not encountering friction or resistance in a physical sense. Instead, the energy you add is increasingly spent on reshaping your relationship to time rather than on boosting your speed. Mathematically, this appears in the Lorentz factor, g, growing significantly as your velocity increases. Practically, it means that each push of the engine invests more energy into slowing your subjective passage of time than into increasing your velocity relative to the outside universe. The universe begins to hint. You may approach the cosmic limit, but you will not cross it. Yet acceleration does more than alter time. It influences the way you feel weight, the way you perceive motion, and even the way space-time itself behaves around you. This is because acceleration is indistinguishable from gravity, a truth encoded in Einstein's equivalence principle. When you accelerate, you create an artificial gravitational field inside your spacecraft. The harder you accelerate, the stronger this field becomes. If you accelerate at 1g, 9.8 meters per second squared, you experience what feels like Earth's gravity. At 2g, your body feels twice as heavy. At 5g, simply lifting an arm becomes an immense effort. Fighter pilots train to withstand such forces for short bursts, but sustained acceleration becomes dangerous. Blood is pulled downward, vision narrows, the body struggles to maintain consciousness. These biological limits underscore a deeper truth. Acceleration presses against both physiology and space-time. The more force you apply, the more the universe diverts that energy into time dilation rather than velocity. Even if your body were perfectly resilient, even if technology allowed infinite thrust, the structure of space-time would keep raising the cost of acceleration. And then there is relativistic mass energy, the idea that as you accelerate, your energy contribution to the universe increases your effective inertia. This added inertia is not mass in the classical sense, but rather the increasing difficulty of further acceleration. Space is not resisting you in the way that wind resists a moving object. Instead, the resistance is geometric. As your world line tilts further toward the light-like direction, the equations describing your motion make it harder and harder to add more tilt. Imagine trying to approach the vertical edge of a graph that grows steeper as you climb. Each step forward yields less horizontal progress. Each step upward requires more energy. Near the limit, progress becomes almost motionless, frozen despite enormous effort. Acceleration at high speeds behaves exactly this way. If you were inside the spacecraft during this process, the universe outside would begin to warp. Stars ahead of you would gather into a bright cone. Their light would blue shift, becoming more energetic. Radiation would intensify. Even the cosmic microwave background, the faint whisper of the early universe, would shift upward in energy. Space itself begins to feel thicker, richer with photons whose wavelengths have been compressed by your extreme motion. Accelerating too fast, too long, carries physical consequences because the energy you accumulate amplifies the environment around you. Space, once dark, becomes filled with intense light and radiation. Dust grains, normally harmless, strike the hull with the force of bullets. Stray atoms become hazards. What once felt empty becomes a river of energy rushing past. Here, the gentle metaphor breaks into something more tangible. Acceleration is not only a negotiation with space-time, but also with the universe's content. The faster you go, the more the cosmos pushes back, not through friction, but through the quiet presence of energy fields and particles. Another limit emerges through Rindler horizons, which appear when you accelerate constantly. From your accelerating frame, parts of the universe become inaccessible, hidden behind a boundary beyond which no signal can reach you. This horizon arises not from physical blockage, but from acceleration bending the structure of space-time. If you accelerate too long, a region behind you becomes forever unreachable, even at light speed. This effect reveals how deeply acceleration alters perception. To an outside observer, you remain visible. But to you, the universe reshapes itself, placing a veil behind your path. The horizon forms because your trajectory through spacetime bends so sharply that light emitted behind you cannot catch up. Even photons lose their ability to reach you if your acceleration is relentless. Acceleration does not only bend time and space, it bends your access to the universe. As you push harder, the cosmic speed trap emerges once more. Energy requirements escalate, time dilates further, horizons shift, radiation intensifies. Every attempt to accelerate begins to fold geometry more tightly, turning the fabric of space-time into a labyrinth designed to slow your pursuit of the limit. Even exotic propulsion systems, ion drives, fusion rockets, antimatter engines, cannot escape these constraints. Their power may push you closer to light speed, but as you approach the boundary, the same mathematics that governs particles, stars, and galaxies gently encloses you. Infinity rises in front of you like a wall made not of matter, but of equations. Yet the most profound truth is that nothing dramatic happens as you approach the limit. The ship does not shake. The universe does not warn you with sound or turbulence. Relativity enforces its boundaries quietly. The closer you approach the limit, the more your acceleration translates into time dilation rather than speed. Spacetime carries an elegance in its resistance. It does not break, it bends. And in that bending lies the universe's message. Motion, energy, time, and gravity are all facets of the same structure. Acceleration is not simply force pushing against mass, it is mass pushing against spacetime, and spacetime gently pushing back. As we drift away from this idea, a new question forms softly at the edge of our path. If acceleration transforms the radiation around us, and if light itself bends under these conditions, then what happens when light travels through places where it cannot keep its usual speed, regions filled not with vacuum but with matter? Part 11. Light speed in water, glass, and air. When light slows down, light can slow in water, in glass, in the atmosphere, and yet the ultimate limit remains untouched. In these gentle pages, we explore why light interacts with matter in ways that mimic slowing, while the true speed limit of spacetime stands unchanged beneath it. To begin, imagine a beam of light drifting through the vacuum between stars. In this perfect emptiness, nothing interrupts its path. The photon glides forward at the cosmic speed limit, the same ancient value it has followed since the first moments after the Big Bang. In the vacuum, there is no hindrance, no barrier, no scattering, only geometry guiding its motion. But now imagine that same beam entering a medium, a pool of water, a pane of glass, the quiet thickness of Earth's atmosphere. Suddenly, its behavior changes. To observers watching from outside, the light appears to slow, bending gently as it passes through. This slowing is not gradual, it is immediate and profound. Water reduces the apparent speed of light by about 25%. Glass slows it even more. Air, though barely denser than vacuum, slows it just enough to matter in precise measurements. This seems puzzling at first. If the speed of light is constant, set by the very structure of spacetime, how can it slow at all? The answer lies in the delicate dance between photons and matter. In a vacuum, photons travel freely, with no need to interact. But inside any medium, atoms crowd the path. Their electrons hover in probability clouds, regions of possibility rather than fixed positions. As a photon enters this landscape, it does not physically collide with atoms the way a ball might strike a wall. Instead, it interacts with the electromagnetic fields around electrons. What we perceive as slowing is not the photon losing speed. The photon always travels at the speed of light between interactions. Rather, the light wave as a whole is delayed because photons are repeatedly absorbed and re-emitted or scattered in ways that lengthen their journey. The photon moves at full speed during each free step, but the steps are interrupted by countless microscopic interactions. It is not the speed that changes, it is the path. This distinction becomes clearer when we consider that the speed of light through a medium is not a speed of individual photons, but a speed of propagation, a measure of how quickly the wavefront advances. That wavefront includes delays caused by the medium's internal structure. Imagine walking across a crowded room. You do not lose your ability to move, but you spend time navigating around people, adjusting your path, pausing briefly as others pass. The speed you walk at remains the same, but the time it takes to reach the other side increases. Light experiences a similar journey within matter. But the slowing of light is more than a practical effect. It is a window into how matter behaves. Each atom in a material responds to incoming light by vibrating its electrons. Those electrons, in turn, create tiny electromagnetic fields of their own. These fields reinforce or oppose the original light wave, depending on the atom and the wavelength of light. In materials like glass, this reinforcement slows the wavefront significantly. In sapphire or diamond, the effect becomes even more pronounced. The structure of the material defines the relationship. Some materials are nearly transparent because their electrons cannot easily absorb visible light. Others, like metals, reflect light because their electrons respond with powerful oscillations that mirror the incoming wave. Still others absorb light because their electrons jump energy levels, turning the light's energy into heat. In every case, the behavior of light within matter reveals something intimate about the material's internal world. And yet the cosmic speed limit remains fixed. The ultimate speed of spacetime, the rate at which information can travel, is never violated. Even in dense or opaque materials, the fundamental speed is unchanged. It is the medium's complexity that alters the effective speed of propagation. This leads to a beautiful truth. Slowing light does not weaken the cosmic speed limit, it highlights it. The universe allows light to take shortcuts in vacuum, but inside matter, those shortcuts vanish. The speed limit stands untouched because the photon itself never slows, it simply waits. These interactions give rise to refraction, the bending of light as it enters a new medium. The greater the slowing, the sharper the bend. This is why a straw appears bent in a glass of water, why lenses can focus light to a single point, and why prisms split white light into colors. Different wavelengths interact differently with matter. Red light passes through glass more easily than violet light. This difference in interaction spreads the colors apart into a spectrum. Refraction is not merely a property of light, it is a collaboration between light and matter. The slowing of light enables many of the technologies that shape our world. Fiber optic cables rely on repeated refraction to guide light across thousands of kilometers. Camera lenses focus images with exquisite precision because of light's slowed passage through glass. Even the rainbow in the sky owes its existence to light's changing speed in water droplets. But there is something deeper hidden here. Slowing light in a medium reveals how the universe communicates. Light is the messenger of electromagnetism, carrying information about the positions of particles, the behavior of atoms, and the shape of the electric and magnetic fields around them. Slowing this messenger affects how quickly matter can respond to changes. If you move a charged particle inside a medium, the disturbance travels outward at the speed permitted by the medium. But the underlying speed at which spacetime allows information to propagate remains the same. This distinction protects causality. It prevents any signal from outrunning light in vacuum, even if it seems to move faster than light's slowed speed within matter. This idea becomes even more striking when we consider Cherenkov radiation, which we explore later in this journey. When a charged particle moves through a medium faster than light can travel in that medium, it creates a shockwave of light, a pale blue glow that reveals the particle's presence. But this does not violate relativity because the particle still moves slower than light in vacuum. It outruns light only locally, within the medium, not fundamentally. In this way, the slowing of light provides room for extraordinary phenomena without ever allowing the cosmic limit to be exceeded. Some experimental techniques even go further, creating conditions where the group velocity of light appears to slow dramatically, sometimes to just a few meters per second. In rare cases, researchers have made light pulses seem to stop entirely, yet the photons themselves remain governed by the same rules. The underlying laws are intact. These experiments demonstrate not that light can be tamed, but that the medium can be engineered to delay its wavefronts creatively. The cosmic speed limit is never threatened. Only the illusion changes. Understanding this difference between true speed and effective speed allows us to see the world with new clarity. It reminds us that the laws of physics operate not only in the vast stretches between galaxies, but also in the quiet waterways of our planet, the glass of a window, the air we breathe. Even in these familiar materials, light reveals its relationship with matter. It shows us how electrons dance, how atoms vibrate, how energy moves. Slowing light does not diminish its beauty. It expands it, showing us the richness of interactions that shape the world around us. And as we reflect on these interactions, another question forms gently at the edge of the journey. If light can appear to slow in matter, what happens when something else, something with mass and charge, manages to outrun light's local speed? What kind of glow does the universe reveal when the messenger is briefly overtaken by the moving traveler? Part 12. Cherenkov radiation, when particles outrun light's local speed. There is one place where surpassing light speed does happen, not in a vacuum, but inside matter. When a particle crosses that boundary, it creates a soft, ghostly blue glow called Cherenkov radiation. Tonight, we drift into how this beautiful phenomenon works without ever breaking cosmic law. Imagine standing beside a pool of perfectly still water in a quiet laboratory. The water looks calm, faintly luminous under pale overhead lights. Yet beneath that surface, hidden from ordinary eyes, particles sometimes move with extraordinary speed. These particles, electrons hurled from radioactive decay, fragments from cosmic rays, can travel through the water faster than light does inside that medium. And when they do, the water emits a faint, ethereal glow, the shimmering blue of Cherenkov radiation. This glow is not simply light. It is a message, a whisper from the medium itself, telling us that something has passed through faster than its internal structure can communicate. To understand this effect, we must return to an idea from earlier. Light slows down when it moves through matter. Photons in vacuum always travel at the cosmic speed limit, about 299,798 meters per second. But inside water, glass, or air, the propagation of light becomes slower because photons interact with the electrons in the medium. In water, the effective speed of light drops to about 225 million meters per second. Particles with mass, however, do not interact with the medium in the same way photons do. If energetic enough, they can plow through water at speeds greater than light's slowed propagation. Crucially, they are still moving slower than the true speed of light in vacuum. They have not violated the cosmic limit. They have overtaken only the medium's restricted version of light speed. This creates a situation similar to a sonic boom, but with light. When an object moves through air faster than sound can travel through that same air, it creates a shock wave. The air cannot relay the information of the object's passage quickly enough, so the object outruns the sound waves it generates. These overlapping waves compress into a cone of pressure that bursts outward as a boom. Cherenkov radiation is the optical equivalent. When a charged particle moves through a medium faster than light's local speed, electromagnetic disturbances in the medium pile up. The electrons around the particle are momentarily polarized, pushed aside by the electric field of the passing charge, and then snap back into place. This oscillation generates light, and because the particle moves faster than these disturbances can travel, the waves overlap into a coherent cone of radiation that spreads outward. This cone has a characteristic angle, determined by the ratio of the particle's speed to the speed of light in the medium. A faster particle creates a narrower cone, a slower one produces a wider glow. The exact shade of blue comes from the physics of the radiation itself. Higher frequency, bluer, light is emitted more strongly than lower frequency light. When viewed inside nuclear reactors, Cherenkov radiation fills the water with a serene, almost otherworldly azure light. It looks peaceful, quiet, almost calming, yet it signals intense energies at play. Electrons are racing through the medium at extraordinary speeds, emitting photons in a continuous cascade. But this is not a violation of relativity. The cosmic speed limit holds firm. The particle outruns only the communication speed within the medium, not the ultimate limit embedded in spacetime. The distinction is subtle but crucial. Light in vacuum sets the universal boundary for causality. Nothing can send information faster than that speed through the fabric of spacetime. But within matter, light is slowed by interactions. A particle traveling faster than light's slowed version in water is not breaking a cosmic rule. It is taking advantage of the medium's restricted propagation while remaining bound by the true limit. The universe permits this. It does so elegantly, without contradiction. Cherenkov radiation appears not only in water but in many transparent materials. Particle detectors take advantage of it, embedding fibers of glass or pools of heavy water inside massive observatories. When high-energy cosmic rays strike Earth's atmosphere, they create cascades of particles that emit Cherenkov radiation in air. Specialized telescopes detect these flashes to study cosmic particles that originate from distant galaxies. In deep underground laboratories, Cherenkov detectors help physicists search for neutrinos, nearly massless particles that can pass through light years of lead without interacting. Though neutrinos rarely collide with matter, occasionally one does, imparting energy to a charged particle that then emits a cone of Cherenkov light. Detecting that dim, swift glow allows researchers to infer the neutrino's presence. In this way, Cherenkov radiation becomes a cosmic messenger, a ghostly signal from processes otherwise invisible. The phenomenon also reveals a profound truth. Light is not the only carrier of information. Charged particles themselves can communicate their presence through radiation when they outrun the medium's ability to respond. In essence, the medium announces their passage for them. This luminous shockwave shows us how the universe handles extremes. It demonstrates that exceeding the local propagation speed does not unravel causality. The particle cannot use this effect to send signals faster than vacuum light speed. The radiation still spreads through the medium at its own limited rate. The electromagnetic field still respects relativistic constraints. Nothing gets ahead of the cosmic boundary. Cherenkov radiation also gives us insight into how different materials shape the behavior of light and particles. Water, for instance, slows light significantly, but does not slow energetic electrons nearly as much. Glass and heavy water produce different cone angles. Transparent plastics used in detectors can be tuned for specific wavelengths. Each material carries its own optical fingerprint, and Cherenkov glows illuminate those fingerprints with exquisite detail. On a deeper level, this phenomenon shows how light and matter are intertwined. The same electrons that slow light's propagation are the ones whose displacement emits Cherenkov photons. Matter restricts light, and matter reveals when something outruns that restriction. The glow itself becomes a reminder: the cosmic speed limit is not simply a number. It is a woven structure of interactions, fields, and geometry. It governs how energy moves from place to place, how forces ripple across space, how particles announce their presence. Cherenkov radiation is one of the few visible expressions of this limit, a boundary traced not in silence, but in soft blue light. That glow, when seen in the depths of a reactor pool or within a dark detector chamber, evokes feelings of stillness and awe. The water shimmers with a color found almost nowhere else in nature, a blue with depth and softness. It radiates a sense of quiet intensity, a reminder that the universe is full of processes more subtle and beautiful than our senses are built to perceive. Cherenkov light is not merely illumination, it is geometry made visible, a map of motion, a glimpse of the dialogue between charged particles and the medium they traverse. And as we let that blue glow fade gently in the mind, another question rises softly along with it. If particles can outrun light and matter without breaking physics, what would happen if we could bend or shape spacetime itself? Could we create a path that shortens the distance, allowing motion without ever surpassing the cosmic limit? What strange shapes might the fabric of the universe allow? Part 13. The early universe. When light couldn't move freely before atoms formed, the universe was a fog too dense for light to travel through. Photons scattered endlessly, trapped in a bright, opaque sea. This chapter follows the gentle moment when the universe cooled, cleared, and light finally found space to run. To imagine this early era, drift backward in time, past planets, past stars, past galaxies, to a moment when none of these structures existed. The universe was young then, only a few 100,000 years old, still glowing from the heat of its own birth. Temperature and density were immense. Matter had not yet settled into atoms. Electrons and protons drifted freely, forming a hot plasma that filled all of space. In this plasma, light could not move freely. Photons scattered off electrons at every turn, ricocheting like tiny messengers trapped inside an endless, brilliantly lit labyrinth. This was the opaque universe, a time when every point in space glowed with radiant energy, yet no photon could travel far before being redirected. The universe was bright everywhere, but that brightness could not escape. It was as if the cosmos itself was wrapped in a thick, glowing fog. In this early era, temperature governed everything. At tens of thousands of degrees, atoms could not form. Every attempt for a proton to capture an electron was thwarted almost instantly by the relentless energy of surrounding photons. A newly formed atom would be struck, ionized, its electron knocked loose again. The cycle repeated endlessly. The universe was too young, too hot, too energetic for structure to settle. Light became the prisoner of this chaos. And yet, even as the universe churned with heat, it was slowly expanding. With expansion came cooling, a gentle decrease in temperature as space stretched. Over thousands of years, the universe's glow softened from searing white to deep red, and then to longer wavelengths still. The plasma grew less violent, the collisions became less frequent, the chaos quieted slightly. But it was not enough, not yet. Photons still scattered from electrons via Thomson scattering, a process that kept the universe opaque. Light remained caged within matter's grasp. Even the idea of traveling made no sense. Every photon's path lasted only fractions of a second before scattering sent it spiraling in a new direction. To a photon, the early universe was a storm without escape. But then something gentle began to unfold, a slow, cosmic calming. As expansion continued, the density dropped. Temperature fell below a critical threshold, about 3,000 Kelvin. At this temperature, electrons and protons could finally join together in stable hydrogen atoms without being torn apart again. This moment is known as recombination, though nothing is truly recombining. It is the first time atoms ever existed. The universe had cooled enough for structure to take hold, and with this formation of atoms, the universe changed character. Electrons were now bound. Free charges, the things that scatter photons, were suddenly much rarer. The fog thinned. Photons that once ricocheted violently found fewer obstacles in their path. The universe became transparent. Light could finally move freely. This transition happened everywhere at once. Across the entire cosmos, photons were released from their confinement. They streamed outward in all directions, no longer trapped by dense matter. For the first time, the universe could see, and for the first time, it could be seen. This ancient light still surrounds us. We call it the cosmic microwave background, or CMB, the afterglow of the moment when the universe became clear. It stretches across all of space as a dim microwave radiation, cooled by billions of years of cosmic expansion. What began as a warm red glow has softened into a faint whisper of microwaves, just a few degrees above absolute zero. Every direction you look, this radiation comes to you from the same era, the moment the universe let light go. It is the oldest light we can ever observe. Not because earlier light did not exist, but because no earlier light could travel. Everything before recombination is hidden behind the cosmic fog, unreachable by photons. The CMB acts as the universe's earliest visible surface, the farthest we can ever see with light. And yet, that surface is not uniform. Small variations in the temperature of the CMB, tiny fluctuations only millionths of a degree, reveal the seeds of every structure in the universe. Galaxies, clusters, and superclusters all began as small ripples in this primordial plasma. Where the plasma was slightly denser, gravity eventually pulled matter inward. Where it was less dense, matter drifted away. These fluctuations are written into the CMB, encoded like fingerprints in the oldest light in existence. But to understand how light traveled then, imagine yourself drifting through that moment of release. Suddenly, the world around you brightens, not because it becomes hotter, but because the light that was once swirling chaotically now moves smoothly. For the first time, photons travel in straight lines. The universe opens. In that moment, the cosmos becomes a vast luminous ocean, still warm but transparent, filled with newly formed hydrogen atoms and the freed light that pours between them. Space is not yet dark. That darkness will come later, as stars ignite and reionize the gases around them. For now, the universe is gently glowing, filled with light that will one day cool into microwaves and reach us across billions of years. This moment, called decoupling, marks the true beginning of cosmic history as we can observe it. The physics of this transition is delicate. The binding energy of hydrogen sets the threshold at which electrons can remain attached to protons. The density of the universe determines how frequently collisions occur. The expansion rate controls how quickly temperatures fall. These factors work together in a symphony so precise that even slight changes would have altered the entire tapestry of cosmic history. Had the universe cooled too slowly, the fog would have lingered longer, delaying the emergence of galaxies. Had it cooled too quickly, matter might not have clumped in the right way to form stars at all. The transparency we take for granted is the result of a perfectly balanced unfolding. Even after recombination, the universe was not completely still. Light continued to travel across regions where matter was not evenly distributed. Gravity subtly altered the paths of these photons, bending them through valleys and over hills of spacetime shaped by mass. These bends show up today as anisotropies, small temperature variations in the CMB that astronomers use to measure the shape, age, and composition of the universe. In this way, the earliest light serves as both a relic and a guide. And yet the most remarkable aspect remains this: the universe was once a place where light could not move at all. A universe filled with glowing heat, but without sight. A universe alive with radiation, but without transparency. Then, in a moment of gentle cooling, it changed. Light found space to run. Photons that had been imprisoned since creation were released into the open. Some of those photons have traveled uninterrupted ever since. They have crossed expanding space for more than 13 billion years. They have stretched with the universe itself. They have grown colder, quieter, softer. And now they arrive at Earth, carrying whispers of the moment the cosmos first opened its eyes. As this ancient picture settles in the mind, a new question rises softly in its wake. If the early universe was once opaque to light, and if transparency emerged only when atoms formed, then how did darkness return, and how did the first stars rekindle illumination across a cooling, expanding cosmos? Part 14. Horizons of Reality When Gravity Slows Light and Time. Near a black hole, the universe bends time and light to their limits. A photon leaving such a region loses energy, stretching into redder and redder wavelengths. Here, we explore how gravity affects the speed of light, not by changing its maximum, but by changing the stage it travels across. To understand this quiet distortion, imagine drifting near a massive object, a star, a neutron star, or, in the most extreme case, a black hole. At first, nothing seems unusual. Space feels still. Light moves as it always does, but the closer you draw to the heart of gravity, the more the universe begins to lean toward the mass. Space stretches, time lengthens. The rules remain unchanged, yet their expressions shift subtly, bending around the presence of mass. Gravity does not pull on light in the familiar sense. Light has no mass to tug. Instead, gravity reshapes the fabric through which light moves. A photon always travels at the speed of light, but the terrain beneath it changes. Its straight path becomes curved, not because the photon alters its behavior, but because space-time itself bends under the weight of mass and energy. This bending is invisible to your senses. You cannot feel the curvature, but the photon responds to it effortlessly, following the shortest route through space-time, a route that appears curved to us. This effect is called gravitational lensing, and it reveals itself when light from distant galaxies bends around intervening clusters of matter. The universe itself becomes a lens, stretching the shapes of galaxies into arcs and rings. Yet this is only the beginning. Gravity does more than bend the paths of photons. It stretches their energy. A photon climbing out of a gravitational well loses energy, not by slowing down, but by increasing its wavelength. It becomes redder. This transformation is known as gravitational redshift. Imagine a photon born just outside the event horizon of a black hole. To escape, it must climb through an immense slope of space-time, one so steep that even light struggles. The photon moves at full light speed, but as it climbs, it trades energy for distance, emerging at a lower frequency. To a distant observer, its light appears faint, smeared into deeper and deeper red until it eventually fades beyond detectability. In this way, gravity darkens even the brightest light, but something more subtle occurs near extreme gravity. Time itself slows. A clock held near a massive object ticks more slowly than a clock far from that mass. This is not a mechanical fault, it is the nature of time. Just as motion affects the passage of time, so too does gravity. Einstein united these ideas into a single principle. Gravity is curvature, and curvature redefines both space and time. If you were floating near a black hole's edge, not close enough to cross the horizon, but near enough to sense its influence, you would experience time normally. Your heartbeat, your breathing, your thoughts would unfold with familiar rhythm. But someone observing you from a safe distance would see you moving in slow motion. Each second of yours might correspond to minutes, hours, or years of theirs. This divergence is not illusion. It is the deep geometry of space-time rewritten by mass. The closer you drift toward the event horizon, the stronger this effect becomes. At the horizon itself, time appears to halt from the viewpoint of an outside observer. A photon emitted outward from this point will never quite escape. Its wavelength stretches infinitely. Its color drains away. The photon never slows, but the shape of space-time denies it the energy to rise further. The speed of light remains constant, but the context, the space-time it crosses, transforms dramatically. This is the key to understanding gravity's influence. Gravity does not change the speed of light, it changes the meaning of distance and duration. Near a massive object, a ruler shrinks and a clock slows. A photon's journey across that ruler takes more time because both time and space have been stretched, not because the photon has failed to reach its usual speed. This phenomenon shapes the behavior of light near any massive body, not just black holes. Even Earth bends light ever so slightly. GPS satellites must account for gravitational time dilation. Though the effect is small, failing to correct for it would cause navigational errors that grow rapidly over time. In this way, even everyday technology feels the touch of relativity. But near a black hole, these effects intensify into something almost surreal. A photon orbiting near a black hole can become trapped in a circular path known as the photon sphere. Here, the curvature is so extreme that light neither falls inward nor escapes outward. It simply orbits, circling endlessly unless disturbed. If you could stand at a safe distance and look toward such a region, the sky around the black hole would appear distorted. The photon sphere would create a ring of light, the boundary where photons skate on the edge of falling forever. This ring, as captured by the Event Horizon Telescope, is not the black hole itself, but the last stable orbit of light. The darkness within is not an object, but a region, where space-time has curved so deeply that light cannot climb out. The event horizon is the boundary where retreat becomes impossible, not because light slows, but because the geometry itself offers no escape route. Gravity shapes even the rhythm of light's journey through time. And yet, from the photon's point of view, if such a perspective could exist, nothing changes. Light experiences no time. A photon emitted near a black hole's horizon and caught by a distant observer might have traveled for billions of years from our perspective. But for the photon, the journey is immediate. The stretching of its wavelength, the slowing of clocks near the horizon, these belong to observers who live within time. The photon does not share that dimension. This contrast reveals gravity's quiet paradox. It reshapes time in ways that light cannot feel, yet we can measure it with exquisite precision. Gravitational redshift becomes a tool for probing the universe. By measuring how much light stretches when climbing out of deep gravitational wells, astronomers can determine the mass of stars, the density of neutron stars, and the power of black holes. Even the expansion of the universe interacts with gravitational redshift, shaping the cosmological models we use to understand the cosmos. In this way, gravity becomes not just a force, but a storyteller. It imprints information onto the light that escapes its grasp, encoding the depth of space-time curvature into the very color of photons. If you drifted away from a black hole and watched the universe around you slowly regain its normal tempo, you would feel that nothing unusual had happened. Time would feel continuous. But the universe would disagree. Your journey would have altered the rhythm of your clock relative to others, weaving your experience into space-time in a way no one else could replicate. And so, as we let this understanding settle gently, another question emerges in the twilight between light and gravity. If gravity can stretch time so profoundly, what happens at the farthest boundaries of the universe, where expansion itself stretches light across unimaginable distances, altering its color, its energy, and even its meaning? Part 15. The question beyond the limit. Could the speed of light ever change? Some theories whisper that the speed of light may have been different in the early universe, or could shift in rare conditions we have yet to observe. This segment explores those possibilities, quietly, rigorously, and with respect for the limits of what we know. The speed of light feels absolute, eternal, woven into the very bones of reality. It is the constant that sits at the heart of Maxwell's equations, shaping electricity and magnetism. It threads through Einstein's relativity, linking space and time into a single fabric. It defines the meter, anchors our measurements, and outlines the cosmic speed limit that no traveler can surpass. And yet, as we look deeper into the universe's past, a quiet question emerges. Is this speed truly immutable, or could it have evolved as the cosmos itself changed? To explore this possibility, we begin in the early universe, at a time when temperatures were immense, densities unreachable by any laboratory, and forces unified into relationships we barely understand. In this primeval era, the laws of physics as we experience them today may not have been fully formed. The constants that define our universe, Newton's gravitational constant, the fine structure constant, and the speed of light among them, might have been shaped by conditions so extreme that they had not yet settled into the values we now consider fundamental. This is not speculation without grounding. It is woven into the language of cosmology, particle physics, and the search for deeper unifying theories. Some models, especially those connected to string theory and varying constant cosmologies, suggest that in the universe's first fractions of a second, parameters like the speed of light might have shifted as the cosmic expansion transitioned from one era to another. These are not changes occurring in everyday conditions, nor ones that would alter the universe we observe today. Instead, they belong to the very beginning, a time when the universe was not yet transparent, not yet cool, not yet settled into the structure that allows galaxies, atoms, and life to exist. But what would it even mean for the speed of light to change? To examine this question gently, we must remember that the speed of light is not merely a speed. It is a relationship between electric and magnetic fields, a consequence of the structure of space-time, and a baseline for how information moves. Changing it is not like changing the speed limit on a highway. It is like changing the texture of reality itself. One way to consider this is through the fine structure constant, a dimensionless number that encodes the strength of electromagnetic interactions. This number depends indirectly on the speed of light. If the fine structure constant changes, then so might the apparent speed of light, or vice versa. Observations of distant quasars have suggested tiny variations in this constant over billions of years, though the evidence remains uncertain, subtle, and open to debate. If these variations are real, they could hint at a universe whose parameters shift slightly over cosmic time. Yet, even if these variations exist, they would not imply that photons suddenly travel faster or slower in any simple sense. Rather, they would indicate that the underlying structure of fields and forces evolves as the cosmos changes. A change in the speed of light, in this context, is not a shifting limit that objects could exploit. It is a recalibration of the rules themselves, occurring slowly, softly, and likely only under conditions far beyond our reach. Some cosmological theories propose varying speed of light, VSL models, to address early universe puzzles, such as how different regions of the cosmos came to share the same temperature, despite being too far apart to exchange signals at today's light speed. In these models, the speed of light might have been vastly higher in the universe's first instant, allowing distant regions to equilibrate before the cosmic horizon shrank to a more familiar scale. When the universe cooled and expanded, the speed of light settled into the stable value we measure today. These ideas are elegant, but they remain speculative. The dominant view in cosmology explains these same puzzles through inflation, a rapid expansion of space itself rather than a change in the speed of light. Inflation is supported by extensive evidence, while VSL theories are still exploratory, searching for observational signatures that could confirm or refute them. Even so, the mere possibility invites us to contemplate the deep relationships between constants. If one changes, others must adapt to preserve the coherence of physical law. A universe where the speed of light shifts without coordination would unravel. Atoms would no longer hold together. Stars would not fuse. Chemistry would collapse. The fact that the universe is stable suggests that if any variation occurs, it happens in concert with other changes, preserving the structure of matter and the unfolding of time. This leads to a profound insight. The constancy of the speed of light may not be a universal decree, but a reflection of deeper symmetries. These symmetries, encoded in the invariance of physical laws, give rise to constants that appear fixed. If the symmetries shift, the constants may shift as well. Yet, in our observable universe, across billions of light years and billions of years, no direct evidence shows that the speed of light has changed in a measurable way. The photons in the cosmic microwave background carry information from 13.8 billion years ago, and their behavior fits perfectly with today's physics. The orbits of planets, the spectra of distant galaxies, the stability of atomic clocks, all confirm the constancy of light within the precision of our instruments. Still, physics pushes boundaries. In some laboratories, scientists have created conditions that mimic potential early universe variations. They have slowed pulses of light to walking speed using ultra-cold gases. They have made light appear to stop entirely by storing its information in atomic states. And in complex metamaterials, they have shaped light's propagation in ways that defy intuition. Yet none of these experiments alter the true speed limit of spacetime. They change the environment, not the constant. If the universe ever allowed a different value for light speed, that moment lies in the deep past, or in conditions so extreme, such as the interior of black holes or the earliest instant after the Big Bang, that we cannot yet probe them. And perhaps this is the quiet truth. The question of whether the speed of light can change is less about motion and more about meaning. It asks whether space-time itself is rigid or evolving, whether the laws we know are final or emergent, whether the universe that formed us is stable by necessity or by history. For now, the speed of light remains one of the most reliable foundations in physics. It anchors relativity. It shapes our understanding of causality. It protects the coherence of the universe we observe. If it ever varied, the change was gentle, ancient, and woven into epochs so distant that only faint whispers remain. As this thought settles softly, a final reflection emerges. The speed of light is not merely a number. It is the quiet rhythm of the universe, the rate at which information moves, the thread that binds space to time. Whether eternal or emergent, it is the constant that allows the cosmos to unfold with beauty, structure, and meaning. And with that, our journey reaches its last horizon. The universe holds its shape through rhythms so gentle we seldom feel them. The slowing of time as we move, the bending of light as it climbs through gravity, the ancient glow released when the cosmos first became transparent, each of these truths rests quietly upon a single constant. The speed of light is more than a number. It is the soft thread that ties together space, time, causality, and the deep coherence of the world around us. Tonight, we drifted through that thread from many angles. We explored why light has a speed limit at all, and why nothing with mass can ever reach it. We watched time stretch and space fold as objects approach the cosmic horizon of speed. We saw how light defines our rulers, our clocks, and our very sense of measurement. We wandered through the early universe, when light could not yet roam free, and followed its long journey across billions of years. We drifted near black holes, where gravity reshapes the meaning of distance and duration, and we listened to theories that whisper of a universe still changing in ways too subtle for our eyes. Through it all, one truth remained constant. Light sets the stage, but the universe writes the story. As you rest now, perhaps there is comfort in knowing that the cosmos does not rush. It moves in quiet patterns, steady, ancient, and deeply patient. The same laws that guide galaxies also guide the stillness of this moment, and the same light that crossed the universe for billions of years now arrives gently to your understanding. Thank you for drifting through this journey. Your time, your presence, and your quiet curiosity mean more than you know. May your night be peaceful, may your thoughts soften, and may the rhythm of the universe guide you gently into rest. Good night.